Hello everyone, welcome to our talk, where this idea spread beyond academia, understanding and focusing knowledge transfer from research to practice.
Nowadays, more and more attention is drawn towards translational research. Large government agencies like NSF, NIH spend billions of dollars each year into basic research, and they hope this basic research could help generate greater applied value. Surrounding this effort, there has arisen a line of research that tries to identify when, where, and how academic research influence science and technological invention. And this line of research first originates from biomedical science area. According to a science in 2017, we could see the transfer rate is pretty low. Only about 10% of NIH grants generate a patent directly, and 30% generates articles that are subsequently cited by patents. So the ultimate goal of our paper is trying to help the science and policymakers increase the transfer rate by understanding the difference between transferred knowledge and non-transferred knowledge. Research on this topic has grown these days. However, there are still some limits. First of all, most of the prior works focus at document level and single domain analysis. But a document entails many ideas, so multiple innovations. It's very hard for us to identify the real innovation driver if we study at the document level. In addition, prior research mostly focused at the document level linkages across research and applied domains. What I mean is the citation and the collaboration network. The network diffusion is a biased representation with coarse reference to innovation. And lastly, most of the prior work focused on successful transfer cases. But there is still a lack of understanding to explain why the majority of scientific innovations do not transfer into technological inventions. That's why we need our studies to understand how innovation diffuses at the idea level. And here comes the outline of our paper. So we first use a text mining tool called AutoPhrase to extract around 1.5 concepts from Web of Science research papers. Then we do some cross-domain analysis. We follow the career of those scientific concepts into patent and clinical trial and try to study the characteristics that make them become transfer concepts versus non-transfer concepts. And finally, we build up a predictive model to forecast a large transfer result.
Here comes our dataset. To represent academia, we used research papers from Web of Science. To represent practice, we used patent documents from USPTO and clinical trials.
We start our analysis by identifying concepts through phrase mining. As pointed out by literature in social science, concept is a broad notion spanning entities and ideas, which refer to terms and phrases that get consistently used. Here, we use AutoPhrase, the state-of-the-art phrase mining techniques through weak supervision. We ran AutoPhrase on our corpus, which resulted in 1.5 million concepts for research papers, 0.32 million concepts for patents, and 0.11 million concepts for clinical trials. We presented some examples of extracted scientific concepts in Table 1. Some transferred examples include Internet, World Wide Web, and interactive visualization, while some non-transfer concepts include European maze, network reorganization, and human capital. As our research goal is to understand what kind of concepts are more likely to transfer, we want to make sure that we are analyzing concepts that we are able to observe the entire developing history, or in other words, concepts that originate in our corpus. To do so, we did burn-in, where we only study concepts that emerged in Web of Science after 1995, even though Web of Science documents can date back to 1900. Through this way, we identified 0.45 million new concepts in Web of Science, where we find 2.7% of the concepts transferred to patents and 11.3% of biomedical concepts transferred to clinical trials eventually, which indicates that transfer is a rare event. We proceed to analyze the characteristic differences between transfer concepts and non-transfer concepts. We first analyze the concept's intrinsic characteristics. As motivated by prior literature, concept's intrinsic characteristics can be grouped into 4 categories: height feature category, bridge positioning feature category, ideation and condition feature category, and science-technology linkage feature category. We find that transfer concepts do differ significantly from non-transfer concepts. More specifically, transfer concepts have more adopters, repeated usage, discipline diversity, are conveyed in more emotionally positive way, have more industry authors, and come from engineering field mostly. Besides concepts' intrinsic characteristics, we assume that how a concept gets co-used with other concepts will influence its transfer likelihood. To test our hypothesis, we analyzed positional differences between transfer concepts and non-transfer concepts by constructing a concept co-occurrence graph, as demonstrated by Figure 3. We find that transfer concepts are placed close to concepts that are already transferred.
Based on the derived features, we proceed to investigate whether transfer can be predicted X years ahead of time. Here, we leverage logistic regression plus recurrent neural network, which achieve 0.81 AUC, indicating that our mechanisms can help explain knowledge transfer to a great extent. In summary, in this work we study knowledge transfer at the concept level from academia to practice, where we demonstrate transfer concepts differ from non-transfer concepts in intrinsic properties as well as relative positions with each other. We also demonstrate our proposed mechanisms can help explain knowledge transfer to a great extent through predictive modeling. Thank you so much for your interest in our work. We are happy to take any questions.